Hola, buenos días a todos. Hi, good morning to everyone. Vamos a dar inicio al primer congreso de física fundamental. Entonces, bueno, la mayoría de las personas aquí ahora, tengo entendido que hablan español, aunque algunos tienen su lengua madre en inglés o en algún otro idioma. Les recuerdo que pueden hablar en el idioma en el que se sientan más cómodo y activar la opción por subtítulos. También se está, se está transmitiendo por YouTube. Aquí les comparto el- para que puedan tener también, compartirlo con sus compañeros y también tener la traducción automática. Entonces vamos a comenzar. Este, Me gustaría mencionar a los organizadores, están aquí presentes. Estamos el doctor Adnan Bashir, la doctora Karen Salomé, Caballero Mora, el doctor Cindy Estrada, y no sé si está el doctor Peter Sloan, y son los que están ahora presentes. Entonces, me gustaría que el doctor Adnan Bashir dijera unas palabras en conmemoración a este evento. Entonces,
Uh,
Anansi, if you are if you are
just
here, you can
oh,
say some words.
yeah, just a moment. Can you hear me?
Yes, we can hear you.
Okay. So let me begin, of course, by congratulating Marco Bedoya, Jorge Mastache, and the team that they collected for taking this initiative to organize this international workshop. It, of course, brings together young researchers from various prestigious universities around the world, in particular Latin America, but not restricted to Latin America, but also Europe and Asia. I hope it will enable all the researchers to engage in discussions on fundamental physics, and it's a very commendable activity that you're putting together. Now, you have mentioned to me as one of the organizers. I really didn't do almost anything, just made some suggestions. But all the work that has been done, I understand, has been done from within University of Chiapas and also the physics department and the MCTP. As you would probably see from the program, there are about 30 talks from participants, which are representing 15 countries, covering areas such as particle and nuclear physics, cosmology, and various related topics, including the phenomenology of these topics. This event promises to be a rich and inspiring exchange of ideas, and it hopefully not only offers international exposure to the participant, but also highlights the role of the Mesoamerican Center for Theoretical Physics and the University of Chiapas on a global academic stage. Unfortunately, although Marco invited me, I was unable to attend this in person while being present in the University of Chiapas. But I extend my best wishes to all the organizers and all the participants. I hope this will not just be the first activity, and it will also bring all of you together. And I hope this workshop serves as a springboard for new and fruitful collaborations among each other. It's not just an opportunity to present your work, it's also an opportunity to learn from each other and to start and embark upon new collaborations among all of you. So that's basically it. Lastly, I would also um, request you to take a moment always to remember those around the world who are less privileged, who are more oppressed, and who are suffer from not only educational disprivileges, but also from basic needs as hunger. And I hope that we always think about them in our thoughts and our actions. And may our work be guided by a broader sense of purpose and responsibility. And that's where I stop. And I wish you all the best during this workshop. Thanks, Marco.
Thank you very much for your words, Anand. Now we have a word by Jorge Mastache. Jorge.
Hola, ¿qué tal? Buenos días a todos. I will speak in Spanish if there's no problem. So, yeah, para mí es un gusto acompañarlos en la inauguración. Muchas gracias a Marco, a Peter, a Adnan, a Karen, a Sendik por el esfuerzo de la organización. El primer Congreso Virtual de Física Fundamental y Fenomenología es un evento que va a reunir principalmente a especialistas, a estudiantes, perdón, a estudiantes de pregrado, también de posgrado y jóvenes investigadores, para que discutan su trabajo de investigación, y eso le da mucha pluralidad a las voces y a las perspectivas de la gente que está estudiando y está haciendo física, tanto en México como en otros lugares del mundo. Hay varias personas que están en España y nos acompañan de otras partes de Sudamérica. Y esto abre a la puerta y fortalece la comunidad científica, tanto científica latinoamericana, mesoamericana. Y este congreso se celebra en un momento especial, que es la conmemoración de los 100 años de la mecánica cuántica, que es la teoría que revolucionó nuestra comprensión del mundo microscópico y sentó las bases en gran parte de la física moderna. Es recordar que hay que reflexionar un poquito sobre cómo el conocimiento avanza gracias a la interconexión entre ideas, que es justo el propósito de este primer Congreso de Física Fundamental. Quiero aprovechar también para destacar un poquito el objetivo que tiene el MSTP, el Centro Mesoamericano de Física Teórica, que es un centro internacional que promueve la investigación de frontera, tanto en física teórica como física aplicada. Y pues quiero hacer un énfasis especial en la formación de las nuevas generaciones de investigadores en la región mesoamericana. Los objetivos en general del MSTP pues incluyen impulsar la ciencia, fomentar la colaboración académica, promover el acceso al conocimiento y pues básicamente servir como un punto importante en la región mesoamericana para extender la ciencia en esta región. Y bueno, pues me despido, no sin antes de nuevo felicitar al comité organizador por el esfuerzo, por la dedicación y por supuesto a todos los participantes que van a dar su charla. Pues sean bienvenidos. Muchas gracias.
Muchas gracias, Jorge. Now we have a word by Dr. Peter Sloan. You are mute, Peter.
Yeah, sorry, they just called me and just the wrong moment. So, well, good morning. First of all, I'd like to just start by saying thank you to Marco for doing all of the legwork, the conference, and also MCDP, which always helps with the administration and the Zoom account and all of this business. So I just wanted to say welcome, and hopefully we can enjoy all the talks together. That's it.
Thank you very much, Peter. Now we have let me see if there is another organizer. No, Nestor. Okay. Okay. Okay, I think the other organizers. Okay, now we have a word by Dr. Cindy Estrada, director of LARCAT here in UNACH. Cindy.
¿Qué tal? Muy buenos días. Let me speak in Spanish, please. Pues es un gusto haber participado en el comité organizador de este evento que involucra investigadores del MCTP y de la Facultad de Física y Matemáticas de aquí de la UNACH, junto con investigadores de la región y del país. Y pues la idea es pues que nuestros estudiantes se enteren de los trabajos de investigación y que se pueda establecer una estrecha colaboración en los interesados en el área, ¿no? Dar a conocer también esta, estas áreas o estos puntos importantes de investigación actual de la física. Eh, Felicitar, aprovechando para los investigadores del MCTP, pues salió a un anuncio esta semana de que la UNESCO ya había autorizado que la transición al maíz. Entonces ahora es Mesoamerican Institute for Science, un centro nivel 2 y pues digamos que es su evento inaugural de este centro, entonces pues es un doble orgullo, ¿no? Entonces, muchas felicidades y pues enhorabuena que todas las actividades tengan a buen fin y se puedan establecer muy buenas colaboraciones. Muchas gracias, Marco.
Muchas gracias, Sendik. Entonces, bueno, me gustaría comentarles nuevamente unos cuantos detalles del evento. No sé si puedes compartir el programa, Alexis, de favor, otra vez. I am going to share some details about this workshop, where here is the program we have, because we have a short time and a lot of participation. We decided to divide the Congress in two parts. One is for the main talks, which is where the speakers are the invited people, Adrian Signet, Yao Shakian, Hugo García Cocoazzi, Ana Julia Mischer, José Ramón Villanueva, Andrés Morales, Saúl Fernando, and Stephanie Raya, and the contributed talks given by Dr. Lizardo Valencia Palomo, Giovanni Cruz Huérfano, Dante Virgilio Gómez, José D. García, and Casel Barra Montiel. So these talks will be broadcasted in YouTube, live transmission. And also we have the contributed talks by students, where we have divided. We will have some rooms. These are simultaneous talks, the yellow one, and the green and the orange one, given by different students from around the world. Okay, if there is no, and remember that this event is being transmitted via YouTube, so you can follow the channel. Here is the link if you want to share with other people. So I consider that it is a good moment to start with the first talk. So Peter, if you can present Adrian. I don't know if it's here.
Yes, I am here, in case anyone wonders.
Okay. Where am I? Okay. Good. So, I'm going to speak in English, pero también quiero decir antes, si tienen preguntas, pues después por la parte de preguntas, puedes escribirlos en español o preguntarlos en español y yo traduzco. Pues. Okay, so it's my pleasure to introduce, after a very long time of not seeing Adrian, a very long time indeed. Adrian Singer did his undergraduate degree and PhD in Zurich in Switzerland, and after postdocs in SLAC and the CERN Fellowship, he spent 13 years in Durham, where he had the dubious pleasure of advising me for my undergraduate research project. Since 2012, he's been in Switzerland at the Paul Schreiner, I can't say it properly, but there we go, Institute, with a professorship at the University of Zurich. He's a member of the Swiss Research, Swiss International Science Foundation, and in the start of his career, he worked on higher energy physics, and now he's working on the in recent times he's been working on the low energy precision. So it's a pleasure to have you here, Adrian. Thank you very much. So we can begin. Thank you.
Good morning, everyone. As you expect me to share the slides, I suppose, is that right? Can you hear me?
Yeah, do you need a permission to say this, share the slide?
I think it should work.
There we go.
You see them now? Is that
Yeah,
fine?
I see that.
Okay, and do you see my pointer that I'm moving around now?
Yeah.
Okay, wonderful. So then thank you very much for the invitation. So what I'm gonna do in the next 40, 50 minutes or whatever is I'll tell you a story about how you go from a Lagrangian to a Monte Carlo code. And I think this fits very nicely to this description of the school from fundamental and phenomenological physics. Now, the Lagrangian is something that we would consider a very fundamental object. And the Monte Carlo code is something that is, I'm allowed to say that because I'm working with something a little bit dirty, a little bit very, very phenomenological. Now, this is where it matters where the cables are and where the screws are in your detector. And linking these two things is something I would like to talk about in the next, as I said, 40 minutes or so. So, I mean, those of you who are further away from this field, I mean, what is a Monte Carlo code? What allows it to do? What I understand by this for this talk, it is something that allows you to compute what I called here fully differential fiducial cross-section for scattering and decay processes, but I will focus on a scattering process. And by fully differential or fiducial, I mean really, when experimenters look at the scattering process, they have outgoing particles, and ultimately they want to measure a cross-section. But there is restrictions. Now there's geometry restriction from the detector. An outgoing particle has to be in a certain angle, otherwise it's not in the detector. It will have to have energy bigger than something, otherwise it's not being seen. As I said, if it hits a cable, you don't see it as well, and then you have a certain efficiency and all these sort of nitty-gritty details. And I will make a case that these things are actually very important to take into account in order to get information on the fundamental backbone of the theorem it has, namely the Lagrangian. So this is what I want to talk about. And the talk has three parts. The first part is why we would want to do that. And I decided rather than give you a general reasoning, I would like to tell you a little crime story, a classical Agatha Christie who's done it. This is related to anomalous magnetic moment, and this is one prime example where you see that in fact these fully differential Monte Carlos are absolutely crucial to actually answer very, very fundamental questions. So that's the part one, why this is, as I said, a crime story. Part two is a bit a more lecture-like style. So I will tell you how this is done. Now, for those of you who work every day with Monte Carlo codes and quantum field theory higher order calculation, this will be fairly boring, I'm afraid. So this is a fairly low-level, general colloquial style presentation. And in this presentation, I focus on low-energy Monte Carlos, not LHC. Many things I say will be very similar for the LHC as well, but because in relation to the crime story I mentioned here, I focus on the low energy Monte Carlo codes. And then part 3, I will show you some results. That's again more seminar-like, and also it's very unlikely that I will have really time to go through this, but I will probably just have a few minutes to do that. That's not a big problem because I will show you where all the results can be found. And really, basically, I want with part 1 and part 2, want you to be able to look at a review we have written recently, a collaboration of about 35 authors, international authors, written about this. And you could then maybe look at the results there and get a better understanding of what this is if you have listened to part 1 and 2. So the chair, if you get worried about looking at the slides numbers here and the clock ticking and think, my God, he will never finish, don't worry, I will skip over this one. That's in the plan already. So that's the plan of the thing. So we go to part 1. Why would we want to do so dirty things? Why wouldn't we just want to think about very fundamental global things? And let me start with two questions related to a Lagrangian. Here it is, and I've written Lagrangian of a quantum field theory because this is what I'm going to focus on. And here I have written the QED Lagrangian because really I will, for the discussion, the remaining one, I will replace QFT mostly by QED, but these two questions are independent of this. And the first question, which is a very important question and a fundamental question, is what is the Lagrangian of the world? No, that is something we all would like to understand. Now, so far, best answer we have for this, it's the standard model Lagrangian. That is a very good answer, but we know this is not the complete answer. So that is one sort of, if you want, the fundamental part of the question related to Lagrangian. Question number 1. This is not the one I will address today. What I will address is the question 2 in the bottom half is, given a Lagrangian, someone says, this is the Lagrangian of the world, or as a hypothesis, maybe this is the Lagrangian of the world. What can we do with this? How can we test it? How can we increase our confidence that this is true, or maybe get some doubts on whether it's true or not? So how do we get from a Lagrangian to an observable? On the dials in your experiment, the LED lights flashing up and down, the counters, how do we do that? So here is a mock observable, it doesn't matter what it is. And if you have this Lagrangian here, and then you calculate very hard, and maybe you think whatever the observable is, this is the blue line that gives the result of that. And you want to calculate this very, very carefully and very, very precisely. And then you want to make a measurement. And you want to make the measurement very, very carefully and very, very precisely. And then maybe the blue thing is what you calculated and the red thing is what you measured. And then you see, it's about okay. It will not be completely different. We would have seen it long before, but it's maybe not quite okay. You have something like this. And then there are 3 options. Option 1, the experiment is wrong, or not quite as precise as people think it is. Option 2, the calculation is wrong, or maybe not quite as precise as we think it is. Maybe there's big error bars here. Or option 3, and that's what we always hope for, it is in fact that the Lagrangian we took as input is not the right one, or not complete. There is plus something here that would make this effective. And so you see these two apparently very different question. What is the Lagrangian of the world? And once we have a Lagrangian, how do we get concrete information out of it? It's very closely related. They play to each other because now you could say, what if there's something different here? Would that explain this, or would it do something different? So that is just to tell you that the things play together. As I said, I will focus on this part here. And I have made here this general example that we measure something precisely and don't maybe quite get what it is. And this is a very concrete example that has been in the news, and in fact, not only in the physics news. This is, you will know this, the anomalous magnetic moment of the muon. This is when particle physics hits the headline, the first line of the BBC or New York Times or something like that. Example that has been around for decades, actually. So it's the anomalous magnetic moment of the muon. So it is a measure of the interaction of a photon with a muon. It doesn't really matter so much for us what it actually is. If you know it, that's perfect. If not, it doesn't matter so much. It is something that has been measured extremely precisely, really extremely precise. It's a frequency measurement, basically, so you can do that very well. Now you can take the standard model Lagrangian and calculate. And most thing you can calculate perturbatively. And indeed, if you look at this Lagrangian here, so what is hidden here is in QED basically an interaction. In QED, more or less the only interaction that we have of a photon with say, an electron or a muon or a lepton. And this is locally proportional to a small coupling. The fine structure constant, you can use the smallness of the coupling and expand this. And now I say, you can just calculate this. The poor people who do this calculation will not like the word just. It's technically extremely challenging, but conceptually you can calculate this in an expansion in alpha and do this. And in fact, this has been done in QED to 5 loops and electroweak to 2 loops to extremely high precision, much higher precision than it's actually needed for the measurement. But then there is also another bit to it, which has to do with hadronic parts. If you look at this diagram here, there is a contribution which has not electrons and leptons, but hadrons, typically pions, but others as well. And for these, the coupling is not small. The coupling is large, and we cannot just expand like this. So it's a non-perturbative contribution, but it's extremely important to get the answer right. And the crime story is the following. So now if we cannot directly calculate or not perturbatively calculate this, how do we get this brown blob? For those of you who know, I'm talking about the vacuum polarization of the photon, but for the moment, you can just think of this as a brown blob that gets into this contribution. And loosely speaking, there are 2 ways. You can get this by measuring the cross-section. So this is an electron-positron, goes into these pions here. So this is the amplitude, this is the complexity of the amplitude. You calculate the cross-section, which basically means cutting these things. Again, the details are not terribly important, but the message is if you calculate the cross-section of E plus E minus 2 hadrons, then from this measurement, you can induce what this blob is, can insert it here and get the result that you cannot calculate. And that is called the dispersive approach. And you want to do that for various values of Q squared, because Q is the momentum that flows through here. So you want to measure this brown blob for various Q squared, and then sometimes it's useful to have an additional photon here because this takes energy away and we get the energy dependence of this brown. This was, until a few years ago, by far the most precise way this could be done. And the answer that you got here is this green lines here. This is many different experiments here, many different ones that have measured this brown blob. Then the brown blob has been put in there, and this has been calculated, and this is the result we get. The red line here, the red thing is what has been measured. You see here 3 measurements over a period of about 20 years, and the measurements are super consistent with each other, but they are 3-4 standard deviations away from it. This is when the BBC came, when the New York Times came. Oh, something is wrong. So maybe we need this here. We need this here to get the difference. And then what happened is people looked at the second method to calculate this blob. And this is something I will not talk about at all. This is a purely numerical, it's lattice QCD. It's a purely numerical way where you can non-perturbatively calculate this blob. Until about 5 years ago, these calculations were not precise enough. The error bar was huge, so that the results were not very useful. But in the past years, there's been tremendous progress been made. And people could calculate this much more precisely. If you take the lattice brown blob rather than this dispersive one, the result you get here is this blue line. And you see it agrees with the measurement. And to make things worse, there was a new experimental measurement on this side here, which is called CMD3, which is also on this side. No, and now this is the classic case that we had before. We are now not sure anymore, is our calcul, so that the red thing is here what we measure, let's say. Now we were fairly sure until 5 years ago that the blue line is what we measure. And all of a sudden, what we calculate, and all of a sudden, or maybe is it the red one? So we're not sure anymore. And the question is what went wrong? And you see here, what is particularly worrying is first, let's even forget the anomalies. Let's forget the red measurement. What is worrying is that the termination of this brown blob between these green experiments here and lattice is different. It's just theory in one way, theory in another, it differs. And what's also very bad is that different measurements disagree. So it is an almighty mess. No? And actually, normally you would think a mess is a bad thing, but I enjoy it. I thoroughly enjoy it. And just to see how small the effect actually is. So what you see here, we just focus on the left-hand side. See, this is the measurement of the interaction strength of a photon with a pion. It's something that enters very much into this blob here. It's called the form factor. We come back to it later on. It doesn't really matter so much what it is, but it's a function of q squared here. I say center of mass energy square root of s, but it's the same as q squared. And what you see here is a yellow band here and here. The yellow band is the measurement of this, the latest experimental measurement, this one here. And all the other experimental results here are what you see here, the blue, the red, the green, and whatever it is. And if you look just at this from a distance, you see, oh, that's pretty good. No, they are all very close together. They are not very different. But in fact, if you look carefully here, just here in this small thing, we have a deviation of about 2 to 3%, maybe 4, but not 2 to 3% or something like that. And here again, tiny differences. And this tiny difference decides on whether we are here or whether we are here. And this decides on whether there is new physics or is no new physics. So, and this is what I find very intriguing as something you could say, oh, but I have more important things to worry about than whether it's this or this. But really, this, in the end, is the key to answering the question whether in the anomalous magnetic moment of the muon we find new physics or not. And if you expect me to give at the end of this talk the answer, what is the solution to the mess? I have to disappoint you. No one knows. No one knows. I think it's fair to say that most people would now say that probably there is no new physics in the anomalous magnetic moments because these things here agree. But no one understands at all why this is here and why this is there. And what I now would like to convince you, it could be, I'm not saying it is, but it could be that this step here has been not done carefully enough. That really the curve here should go along the red line or not. That is one possible explanation, but no one knows what really happens. So it's an almighty mess, which I think it's a beautiful mess. Normally, we want to agree theory with experiment, but I think in particle physics, we're now at a stage where we're happy that this is not the case. So I hope with this I have convinced you that it is actually important to look at these nitty-gritty details, these phenomenological applications, and look at everything. And now I go to a more lecture style thing on how this is done. Now, obviously, this is something where you would have to take a 1-year course with 4 lectures a week to really do this. So I will try to give you a flavor. And I try to balance this a little bit for those who are more familiar with this, that they get a little bit something out of it, and those who have never heard of it at all, I get that close also a little bit of a flavor. So how do we calculate this scattering? processes. Now quantum mechanics tells us we have to start with the amplitude. And the amplitude is really, we start with an initial state and a final state, and here is the S matrix. And the basic assumption of scattering theory is that I is an initial state that was free at a very early time, and F is a final state that will be free at the very, very late time. I stress this because in quantum mechanics, you learn this, and then you forget it. And then you do calculations, and we will do that, and then at some point you get punished. So remember this free, this basic assumption of scattering theory. We will see we will violate this, and then we get punished by this. But that's what we do. And then we have the amplitude. Now, how do we calculate this? Now we write the amplitude as e to the Lagrangian. We split it into a free and an interaction part, and we expand in alpha if alpha is small enough. So that's the classic perturbation theory approach. And you know, this gives you Feynman rules. It gives you Feynman diagrams. You have to evaluate, we have to generate these diagrams, evaluate them. No one does this by hand anymore. No. When I was a PhD student, the first question was always, did you forget a diagram? No one forgets a diagram anymore. Our processes have hundreds of diagrams. We don't draw them by hand and calculate them by hand. You have no chance to get it. This is all automated and generalized. Once we have this, we have the amplitude, and then in Q we have learned for the probability of the absolute amplitude squared, and we integrate over the phase space, and this gives the cross check. So that's the idea. Now you think, but that's trivial. Why do we even need to listen to a talk to this? And that's what I want to tell you now, why in fact it is not quite as trivial if you want to go to really experimental observable. And the example to do that, to explain this is take the process electron-positron goes to a muon pair. This is one of the processes that I have mentioned before. Just to quickly go back. Now, here is the processes I mentioned. You might wonder, why would I even need the processes with the muons in the final state rather than just the pion? Because it's only the pion with the brown block that we cannot calculate. The reason you need these processes is that because in the same experiment where you measure this one, you also measure this one. And you want to make sure that you get this absolutely right, otherwise you don't trust this. You want to measure the luminosity, you want to measure acceptances, you want to measure efficiencies with this process to be sure you got this one. So really these two go hand in hand. You have to understand this process, you have to understand this process as well as this one, although you have no chance to get the details right. So really the two come together, even though technically they are very different to calculate. But this one is a simple one. Here we can just QE. And so here we go. We start at leading order. The simplest thing, we have one diagram. Here it is. I write A, the amplitude. I write a little 0 for leading order. I take the complex conjugate of the amplitude because I want the absolute value of the amplitude square. I draw it like this, and I have this little dashed line here, which is a phase space integration. And then I get the amplitude squared, and I integrate it over the phase space, and I can calculate the total cross section. And this is the result: 4 pi over 3 alpha square over s. And you think, come on, that cannot possibly have been very difficult. And indeed it isn't. This is something you don't want to envelope in 10 minutes or something. And this cross-section is proportional to e to the 4. I've drawn here 4 red blobs, which is a coupling e, and e square is proportional to alpha, and it is proportional to alpha square. Remember alpha. This is an academic quantity, a total cross-section. That has very interesting information in it, but it is just not related to any experiment. No experiment has ever measured a total cross-section. No experiment will ever measure a total cross-section. Whenever an experiment gives you a total cross-section, what they do is they measure something with some cuts and then extrapolate it to a total cross-section. And how do you extrapolate? Exactly, with Monte Carlo. What experiment really measures is what I've drawn here, a differential cross-section. So you take the amplitude square, you integrate it over the phase space as before, but now the big difference is this thing here, that is the definition of the precise observable as a function of final state momentum. And typically that's neglected, but that can be very complicated. Not here, because it's only 2 final state particles, but if you have n final state particles, and typically you have more than 2, then you have 3n-4 degrees of freedom here. And you have very complicated cuts, boundaries. Remember, energy bigger than that, angle smaller than this, but bigger than that. Except if it goes this way, then it's a bit different. It's a horribly complicated phase space integral. And this is done numerically. You don't want to do this analytical. And this is what Monte Carlo tools do. You calculate, typically you calculate this analytically, and you calculate the phase space numerically. But again, this is a leading order calculation. This you can do in an afternoon, not a problem at all. But leading order is not good. Remember, alpha is order 1/100. We want to have something that is certainly better than 1%, really better than 1%, because 2% is a huge effect for us. So we have to go beyond that. We have to calculate next to leading order. So let's do that. Let's calculate the one loop amplitude. I've drawn one here. There are many more diagrams, but I just draw one. You see 1, 2, 3, 4 couplings times the 3-level complex conjugate amplitude. It's e to the 6 is alpha cubed. It's roughly 1% of the leading order result. In truth, it's a bit more. We'll come back later to that. It's typically a few percent of that. So what's new here? What's new is here you have a loop integral, a loop diagram. And that means it gives loop integrals. And just this part here, I've drawn a bit wider. So here it is. We have the momentum. So we have the incoming momentum is fixed by the experiment. P1 and P2 are fixed. In that sense, this is what you see, what you measure. But you see the momentum K of this photon that is exchanged here is free. It can be anything. And then quantum mechanics, it tells you have to sum over everything. So here you have to integrate over K. Then let's do that. Let's just look at this one diagram. Now, those of you who have done Feynman diagrams, then let's look at what this vertex diagram, it's called a vertex diagram, is what it is. And we look at it in the limit K goes to infinity. So from this propagator, we get a K slash. From this propagator, we get a K slash. You get other things as well, but I don't care about the other things because I'll just look at K to infinity. From this propagator, you also get a K plus P1 squared minus M squared, but I don't care about M because K goes to infinity. You get this here from that propagator, and the photon propagator is the 1/K squared. And now again, because the P's are not important in the limit K to infinity, so I count the powers of K. I have 6 powers of K in the down there. What is down there? Numerator, the denominator. And I have 4 plus 2, 6 powers of K in the numerator. So I get this integral here. And I have to integrate to infinity. And that doesn't look good. No, these are divergence. So this integral is divergent. But that's, of course, well, no, it's an ultraviolet divergent, and we have to renormalize this. The mistake what we have made conceptually is that when we look at our initial Lagrangian at the very beginning, we thought of this as the mass and of the alpha or the E that's hiding in there as the coupling. But that's just not true at all. This M here is an artificial theoretical parameter with no direct phenomenological or physical significance. And if we express our amplitudes in terms of these quantities, we do something silly and we get punished by ultraviolet divergences. What we should do instead, we should use good quantities, more physical quantities or renormalized quantities. And if we express everything in terms of that, these ultraviolet divergences will finish. Will disappear. So that all these divergences are absorbed by this renormalized quantity. Sometimes people say this is cheating. That's just not true at all. It's not being silly. That's what it is. So if you express one physical quantities in terms of another physical quantity, they're all neutralized. Yes, someone wants to say that? Does someone have a question or? Okay, so let me move on then. Now let's look at the same diagram again, but in the infrared limit. So now let's look at this again in the limit k goes to 0. Now I take again here the d4k from the loop integral. In the numerator, I'm not interested in k anymore. It goes to 0, so there are just p's and m's here. And if I look at the propagators of the fermion, I have this here, k plus p1 square minus m square, but p square is m square, so it's only this one here. And in the limit k to 0, this is less important than this, so this is the only thing that survives, 2k p1. I do this for the two fermion propagators and the photon propagator. Now I get this here, 4 powers of k in the numerator, and 1, 2, 3, 4 powers of k in the denominator. I get something like this, with the boundary 0 now, and that's also bad. It's a logarithmic divergence now, not for k to infinity, but k to 0. This is an infrared divergence. This was called long, long ago the infrared catastrophe, because it seems to be infinite. And to tackle this or look at the solution of this, we look at something very similar to this now. Don't blink, because what now happens, I look at this. I look at an apparently different process. I look at the process E plus C minus mu plus B minus with an additional photon. And let's go forth and back a little bit. Let's look at this photon here. Before, the photon was virtual here. And now, oops, I have to say okay here. And now it is real, okay? So we do not have a loop diagram anymore. We do not have a next to leading order correction, but we have a leading order correction, but with one more photon. We do not have a loop integral anymore over the photon momentum, but we have a phase space integral over the photon momentum. But the power of alpha is the same. The number of red dots is 6 on both sides. Both is alpha cubed. And if you now look at this so-called real diagram, because the photon is real, and you look in the limit k to 0, you can do what you have done before, and you get nearly the same structure. Again, let me flip forth back a little bit. Here we had this structure, a loop integral with 4 powers of k. Now this is not the loop integral anymore. It's a phase space integral, which is d3k over 2 omega. Omega is the energy of the photon, so it goes like k squared and not k to the 4. But we also have no photon propagator anymore. So we have d2k over k squared, but this is also dk over k, so it's also infrared divergent. And now you might think, but that hasn't helped a lot. No, we had an infrared divergent here. Now it comes up with something else, and this is also infrared divergent. How would this possibly help? Now here is the miracle. This is the Jenny-Frauci-Sura miracle. If you add these virtual corrections and these real corrections, both of them are separately infrared divergent, but together they are finite. That divergence is cancelled. This is not so surprising. If you look at this and this, there's a very similar structure here. And in fact, luckily the sign changes. And if you add both together, it is finite. Now, what is the origin of this infrared singularity? And that is what I said before. It's with this basic assumption of scattering theory. The state I in QED is never free, because we have Coulomb interactions, and you can wait as long as you want. You go into the future and the past as much as you want. This I and F, the initial find, they're never free. So we violate the basic assumption of scattering theory, and we get a slap on our finger, and the slap of our finger is the infrared divergence. But we can save it by saying, well, really, we should, our external asymptotic state, we cannot distinguish a muon, one muon, from a muon with an arbitrarily soft photon. Remember, the photon is massless. It can have as little energy as it wants. And whatever detector you build, conceptually, it can make this photon energy so small that you will never see it. So really, a proper definition of this the initial final states would be a lepton with a cloud of soft photon around this. And it's all related to the fact that the mass of the photon is 0. But now we're very good at this. We can combine this consistently, and then the infrared singularity is cancelled. That's good theoretically, but conceptually this is still difficult. Remember, we want to make these phase space integrations numerically. These amplitudes here get more and more complicated. This one still is not so complicated, but if I have more complicated process, it gets more and more complicated. I have a complicated integrand, very complicated boundaries, and to make things worse, it's divergent. So how do we do this numerically? Well, we have to regularize it, and I cannot go into details. There's different ways. You can know, I said here that the problem or the issue is that the photon is massless, so you could give a fictitious mass to the photon as regulator, and then the singularities are logarithms of m gamma, and once you combine real and virtual, you set m gamma to 0, and then that's fine again. Or you do dimensional regularization, you don't integrate in 4, but in d dimension, and then the singularities are poles 1 over d minus 4. Once you combine real and virtual to set d to 4, you do this like that. And in order to deal with the integrations, again, there is different methods, but the idea is always the same. You have a very complicated divergent integral. What you do is you split it into something simple divergent and something even more complicated but finite. So you basically subtract the singularity and add it back, or you isolate the singularity and look at it separately. And then you can use this bit to combine with the virtual correction. And this one is even more complicated as before, but it is finite. So we can use Monte Carlo numerical integration to deal with it. And you can do this in a process independent and systematic. So that is the idea. But you see, things get more complicated. Now you think, oh, okay, that was tough. We had ultraviolet singularities. We can deal with them. We had infrared singularities. We can deal with them. And there is another monster around the corner, and that is collinear emission. I call it here collinear pseudo-singularities. This is one of the biggest differences in my talk in QED compared to QCD. So let's look at that in QED. So we have here the amplitude again, as before. We have now this photon here. But we now don't assume that the photon becomes soft, but let's see what happens. It becomes very collinear to this P1 of the muon. And let's write down the momentum here. The photon is massless, so it's omega 1 n. N is the unit vector in the direction of the photon. P1 is the photon of the muon or the electron, whatever. It's E1 n1 times beta. Beta is the velocity of the thing. If the muon was massless, beta would be 1. And now let's look at this propagator here in between, k plus p1 squared minus m squared, inverse of it. Again, I do what I had before, it's 2k p1. And now I plug this thing here, and what I get is 2 times the energy of the muon times the energy of the photon times 1 minus beta. And it's 1 over this. No, it's the denominator of the propagator. If the muon was massless, that would be singular. That would be a collinear singularity. And those of you who do QCD will be very familiar with this. In QCD, typically the masses of these particles are all set to 0 with a collinear singularity. In QED, we keep the mass. We keep this m. And so we don't have a singularity, but we have a logarithm again. Now, this logarithm comes with a coupling. So we have a term at next to leading order that does not only have an alpha, but has this logarithm. And most applications, the masses are much, much smaller than what is q squared. This is the center of mass energy of the process, let's say. So m is much smaller than q squared. No, the mass of the electron is 0.5 MeV. Q squared is 10 GeV or something like that. So this logarithm is large. Alpha is small, but the logarithm is large. So this things is called large logarithms. And when I said at the very beginning, corrections are not really 1%. As you would expect from alpha. It's not 1 over 137, but it's 1 over 137 times a large logarithm. So typically QED corrections can be 4, 5, sometimes even 10%. Okay, but that's what you hear. And again, notice is the difference between QED and QCD. If I have time at the end, I explain why in QED we really don't want to set the masses in 0. In QCD, you set it to 0 because you have these singularities here, but you combine this collinear emission into a jet, so you put everything together. But in QED, we reach much more differential. You want to distinguish the photon goes here, even if they're collinear to start with. If you have a magnetic field, the electron goes there and the photon goes there. So you really see these things. These logarithms are being measured. But now you worried at NLO. No, you have this NLO alpha times this 4, 5%. And let's go back to our crime story again. 2% is considered large, 3% is considered large. So alpha times a large log is not good enough. Even though we suffered a lot of sweat and blood, it's not good enough. We have to go beyond next to leading order. We have to go either next to leading order. So that means 2 loop diagrams times tree-level amplitude, or 1 loop diagram times 1 loop diagram. I haven't put in the red dots here, but if you count them, 2, 4, 6, 8, this is alpha to the 4. So it's 1 power more. Now here we had alpha cubed at NLO, and NLO we have alpha to the power 4. So that would be the double virtual contributions. But we also have real virtual one loop diagrams with 1 additional photon, or double real tree-level diagrams with 2 additional photons. Now you can believe me that the expressions here do not become simpler when you do a 2-loop integral. No? This is ultraviolet and infrared divergence. This is ultraviolet and infrared divergence. This is infrared divergence. You renormalize, the UV singularities go away, but then you have to combine all 3 of those to also get rid of the infrared singularity. So this phase-space integration is really delicate because you have to subtract everything that comes from the infrared singularities here and munch it into these 2 bits and pieces, and you have to do this fully generically. You do not specify what your observable is because you want the experimentalist to decide whether the cut on the outgoing muon is 17 MeV or 170 MeV or 173 MeV, and whether the angle is between 13 and 70 degrees or between 13.5 and 17 degrees. So you have to be completely agnostic about this. So you have to do this in a very universal way. But it can be done because the structure of the singularity is universal, but it is tricky. Indeed, NLO is very tricky because also you have to remember those of you do QCD calculations, we keep all the masses. We cannot set masses to 0, and loop integrals become extremely difficult if you keep all the masses. So the integrand, the amplitude squared will become tremendous. I'm talking expressions with hundreds and hundreds of megabytes. And in a Monte Carlo code, you have to evaluate this millions of times to get numerical statistics well. So you see, it becomes a real effort to do this. But that's the state of the art. Now you can say, this is too much. We want to do something a little bit more gentle. What you can do is you can actually just add next to leading order, not the full next term, but just dominant approximation. Just here, I told you that the collinear emission is dominant because of these logarithms. Then you could say, why bother with all of this? We just take the collinear approximation to this. So we approximate an incoming electron, say, with an incoming electron with emissions of many collinear photons. This is called a parton shower. That is a very good approximation to do as well. Or you can make a soft approximation. This is called YFS again. So YFS stands for Jenny, Frau, Gisura. This is the people who've realized this miracle here in somehow the first systematic way. And you can use this to have the dominant soft approximation. So you approximate the matrix with additional many soft photons. So the good thing is this one has a few things that this one doesn't have, and this one has a few things that this one doesn't have. So really, it's a different approximation to the next order, and comparing this is a very useful to do. So that was QED. And if all of this wasn't bad enough, it gets worse. Because remember, we do not only want pions here and muons here, we also want pions here. And the big problem with pions is they are not fundamental. So really, if you look at the interaction of a photon here with an electron or a muon, this is point-like. Now you know it's a E times gamma mu or something like that, gamma matrix. But the interaction of a photon with a pion has this blob here. This blob is called the form factor. And in fact, this was the thing I showed here. This is a measurement of the form factor, reduced measurement of the form factor. And this form factor depends on Q square, which is the momentum here. And if you look at it depends on Q square, again here I write square root of S rather than Q square, but here is Q square. And here is the form factor. And you see the dependence is highly non-trivial. It starts about, you probably can't see this, it starts about 1, it goes up to nearly 100, and it drops to nearly 10, to nearly 0, 10 to the minus, and it goes up again and whatever. So it's a very complicated structure of this. That's not a problem for this diagram, because you just multiply the point-like diagram with this form factor. It gets a bit more problematic if you have 2 photons, then you have 2 form factors, but that's also okay. But it really hits you when these blobs are in a loop. Now here, this is a box diagram, when you have a box, photon, photon, pion. Here is a loop integration. So that Q square now is a loop integral. So I don't know who of you has done a normal box loop integral. It's not so nice to do, but these days it's trivial. But if on top of that you have this factor, this horrible factor in the loop integral, not nice at all. You just can't do it analytically. It's impossible. Then you say, okay, let's do it numerically. But remember, we have singularities. Just do it numerically is also not simple. You have to single out the singularities again, deal with them separately. And whatever is left, you have to do numerically. You have to do efficiently. You have to do quickly. You have to evaluate this millions and millions of times in the Monte Carlo code. It has to be fast, stable. Sorry, this is basically at the moment state of the art where we're working on. It doesn't get easier if you have an additional photon here, as you can imagine. Things become arbitrarily complicated. So that's the status where we are. And now I have about, I think, 5 or 10 minutes to show you a few results. I will just highlight a few that all the things I said actually will enter. Now the results are taken from this Radio Monte Carlo 2 initiative. So this is, you can here find the archive number. So this is a collaboration of about 30 to 40 people, many different countries. There's many different people who have written Monte Carlo codes with different kinds of approximations. Now some do this here, others do this, others do that for different processes, different methods. And the idea is really to sort out this mess. That's the idea, to sort out this mess here, sort out this mess. This has been going on for a few years now. And we have written out this report, and you can look at many more figures. And it's an ongoing report. So if anyone thinks, oh, that's thrilling, I want to join this, then the thing is still going on. So let me pick experiment number 1, CMD. That's one, sorry for flipping forward and back, but I want to show you this. This is the new one. This is this one here, where everyone was there. And this one is here. Okay, so this, they measured E plus E minus goes to pi plus pi minus. So let's just look at the top panel. This is the scattering angle of the outgoing positive muon. Theta plus is the scattering angle. It's at the low center of mass energies, and there are many, many cuts. I have not even written them down here. You find them in the reports, but you have many cuts. And you see that here, because the result is basically 0 and then jumps up and then goes to 0 again, and that is the reason because of the cuts. The next thing you see here, there are many, many codes that calculate this in different ways. Okay, so many people are involved in this. And then let's go to the middle panel and let's compare those curves that are there. So these are the codes that pretend that they can do this well. And if you look at this here in this region here, the difference between the codes here, you show the ratio, and you see it's the difference is small. It's 2 per mil or something like that. And another thing you see is the gray dashed line is a next to leading order calculation. The gray solid line is a next to leading order. And you see the corrections are small, 2 per mil or something like that. And the blue and the brown lines are next to leading order plus soft approximation or parton shower approximation. You see they're all very close together. And so you say, this we have under control. That looks very convincing. It's a process, 2 particle in, 2 particle out. And in here, it looks super stable, well better than 1%. So I would say, fantastic. But now let's go to another process. Let's go to one where we have 2 to 3. So that's Chloe. That's one of the other experiments, which was on the lower side of the thing. Now here we look at the invariant mass of muon pair, whatever it is, doesn't matter. Again, you see many codes have calculated this. And now here you see it starts to wiggle more, okay? In particular, if you, for example, let's pick out the brown line here, which is a next to leading order calculation. Here we do not have next to leading order. We only have next to leading order. And we have the gray line here, which is another next to leading order calculation. And you see the differences, if you look here, nearly 1%. It is technically understood where this difference comes from. It has to do how we include vacuum polarization correction. So technically it's understood. We can technically make this completely agree. So it's not a sign mistake or someone forgot a factor of 2. It's 2 slightly different approximation and next to leading order. But you see the difference is 1%. And remember, 1% is a lot. So this is not good enough. We have to go beyond that. This is not really good enough. And it gets worse. So let me pick maybe another here. This is now BESS. This is at even higher energies for GeV. This is also one of the experiments which is on the wrong side. And again, this is now the invariant mass of this with many different cuts applied. And let's just look at the bottom panel. But let's look at the dashed line. This is a leading order calculation. We know that's not very good. But we have different next to leading order calculations, which are these here. And we see the ratio. You see the next to leading order calculations technically agree very well with each other. That means we probably have not made a mistake. The next to leading order calculations are technically correct. Which sounds trivial, but it is really important to make this. That's why it's useful to have different codes, because you never know. We're humans. We do make mistakes. And if you have completely different codes that agree, that is very comforting. But you see the corrections from leading order to next to leading order are 10%, not 1%, 10%. And in the end, we want to be better than 1%. So if the next to leading order corrections are 10%, you really want next to leading order. But for 2 to 3 processes, they are not yet available. We are working on this, but it's not yet available. But you see here, currently, the theoretical description of 2 to 3 processes is delicate. And here just an example that we also can do pions. I told you pions are more difficult. That means the quality of the approximation is currently a little bit worse because we cannot do the most complicated things at the moment. And here again, this is cos of the scattering angle of the positive muon. It doesn't matter so much what it is. Here is the distribution. And then that's a plot where I want you to look at. The brown line and the blue lines are currently thought to be sort of the best codes, but you see they differ by 3% here. So this observable is not known theoretically better than 2 or 3%. And then you think if the theory error is 2 and 3%, even if you assume that the experimental one is 0, how can you make sure that here, this tiny little difference here is not just something that we should calculate more carefully. So that's something that really has to be investigated carefully. That's what the plan we want to do. I'll skip over this, and I'll skip over this. You find many more plots in the report. So let me wrap up. So some of the key messages I would like to give, there is really a very big difference between what I call academic and experimental observables. Now I have mentioned these total cross sections. Now I don't want to be negative about analytic calculation of total cross section. They contain a lot of important information. It's a very useful thing to do. But if you then want to compare to experiment, you have to do more. You have to do the dirty nitty-gritty things. You have to worry about what the efficiencies and things like that. So you have to be fully differential. And this is a heavy price to pay, as I tried to convince you. And these Monte Carlo tools, and you see many are working on this. I have not mentioned the LHC ones. There are also many groups working on Monte Carlo tools for LHC. They do connect the fundamental ingredient directly to a measured quantity, so very extremely useful. And on the low energy frontier, what we currently have, we know 2-2 processes at next to leading order, or improved next to leading order. So that is next to leading order with a parton shower or with multiple soft emissions. And we know 2-3 either at next to leading order or the leading order ones improved with this parton shower things. And as I tried to convince you, this one looks good. We're happy with this. I mean, the whole 2-2 is okay. We have 2 per mil uncertainty, so that's okay. But this one here is in my view, really question. And the devil is in the details, not just doing the calculation. Very often it happens, and then you realize you would have to run your code for 20 years to get something, so you have to do something about this. And so for me, that the big question for low energy Monte Carlo tools now is are the available tools sufficient to reliably determine the hadronic vacuum polarization? So this brown blob I mentioned at the beginning. This is not an academic question. It is a question whether we have new physics in a magnetic moment or not, or what the hell is going on with this. No, I mean, again, just to quickly go back, no, I said we had 3 options when we look at this one here. We had 3 options. Either the measurement is wrong. It's very unlikely. They really confirm each other. This is a textbook example of better statistics and different experiments. It's very unlikely the experiment is wrong. The other one is that there is new physics. It's now fairly unlikely that it's new physics. It's the lattice agrees, this experiment agrees. It could be, but it's not so likely anymore. Then the other thing is the experiment is wrong, but it's not just one, it's 5, it's 10, it's many, many experiments. They're all wrong. And then the last one remaining, maybe the theory calculation wasn't quite good enough, but I'm not allowed to say this aloud because some people disagree with this statement, but at least I think it's something that has to be investigated very carefully. So the answer of this will be given in a few years, and what we are going to do is the 2-3 calculations better at next to leading order or next to leading order with parton shower and IFS. This is what the thing is. And I hope I did conceive a little bit of excitement of this hard, tedious work, so that you hopefully some of you agree that this is a worthwhile thing to do. And with this, I would like to finish.
Well, thank you very much, Adrian. That's a very nice talk. Well, while other people are thinking of their questions, if I could ask you, so obviously I haven't done any form of phenomenology for ever. So I'd like to ask, is there any sort of guarantee that the next to leading order calculation will give us enough precision, or could it be that you need even more?
So basically what you're asking is, can we get an error estimate on our calculations? No, and this is notoriously difficult because, you know, we do a perturbative series, and I give you, now let's assume we calculate, you get 1 plus 0.1 plus 0.03. So now we look at this. Good. Now, if you knew what the next term was, you would have calculated it. So you don't know. And then you have to try to guesstimate what the next term could be. Now, there are a few things you can do. And those of you who do LHC know what they do. They vary the scale and look at the uncertainties from this and that. But all of this is really very, very poor man's SES. There is no way to statistically really assess the error reliably. So what you can then do is you look at soft approximations, but it is extremely, extremely difficult. And in fact, this calculation we have now have estimated the error, and it turns now out that they have underestimated the error. It happens often. You think this is the error. Someone does the calculation, and oops, it's bigger. No, it is. The honest answer is not reliable. No, not reliable.
So essentially, the way to go would be just to carry on until you get some sort of
I mean,
relationship with observation.
if you want to be super conservative, you could say my error is the size of the last calculated contribution. No, that would be super conservative. But then that, I mean, if that fails, then you're really very, very, there are actually cases where this fails as well, but not so much in QED. So that would be a super conservative error estimate.
Okay, thank you very much. Do we have any questions for Adrian? I don't know how to organize this. If you want to put your hands up, and if you want to speak in Spanish, then I can translate.
Yeah, I would need a translation actually.
Si quieren preguntar en español, y pues hago mi mejor esfuerzo para que ya es traducido bien. O ya están. Marco?
I have a question, but I think I can handle in English.
Excellent.
Thank you very much for your talk, Adrian. I just have a little question. So you consider that this difference in the experimental and theory value is more because we need to improve our theoretical computation, or if there is any possibility to new physics? What is the chances?
3 years ago or 4 years ago, I would have said, I don't know at all, and many people would have said it's new physics. But now, with the new lattice result and the new experimental result, one thing is clear. Within the dispersive approach, these experimental results, they contradict each other. So irrespective of whether there is new physics or not, there is a big problem in the low energy experiments E plus E minus to hadrons. And now we have two methods to calculate this brown block. The lattice one, which so far seems to be very consistent and gives a result in agreement with the standard model. And the other one, the dispersive one, with the cross sections, which is inconsistent among itself and gives a result that does not agree with standard model. Now, which one do you believe? I mean, logically, it is a possibility that still there is new physics and the other one is wrong. But, you know, I mean, one thing is consistent and agrees with the standard model. The other one is inconsistent in itself and disagrees with the standard model. So most people tend to think it's probably not new physics. But we don't really know. We don't really know. I think we have to understand what went wrong in the other approach. And only once we understand what went wrong in the other approach, and it gives the same as the new approach, only then I would really say, no, there is no new physics. At the moment, one can argue.
Okay. Thank you. Thank you very much. Okay. That is that was my question. Thank you.
Yeah, thank you.
Well, do we have any more questions from the audience? If not, I just wanted to ask a small question, which was, with this sort of reduction in the possibility of it being new physics that's causing the anomaly, or if there's no anomaly, does it also reduce what we could say about any new physics? I mean, does it sort of, even if there's a small contribution from new physics, we wouldn't be able to then say anything about what that new physics could be?
Yes. I mean, it's always more difficult to exclude something. But if you take, for example, a set prime or something like that, no, and then in the parameter space, you can exclude things because you know that would give you a contribution to the anomalous magnetic moment that is so big that it would have been clearly shown. Now, you can play devil's advocate. Maybe there is two set primes and one cancels the other. No, I mean, but no, at some point you just have to hold up. It's enough. But you see what I mean? You can always, and people try to trick it. And people have actually thought whether there is new physics in E plus C minus 2 hadrons. That no, we do a calculation in lattice QCD. We get something different than the experiment. Oh, maybe there is new physics in the experiment, which of course is not in the lattice, but in the. But they have tried to make anything conceivable, and it really fails, because if you put in new physics there, it's at very low energies. It would show up somewhere else where it doesn't show up. So it becomes very constrained in that sense. So yes, I'm afraid if it should really be established in a few years that there is no new physics in the anomalous magnetic moment, it also means that many models will peacefully die. Or at least that the parameters play so. You can always make these particles heavier and heavier, the coupling smaller and smaller and smaller. But at some point you have the perfectly decoupled particle, which you can never exclude. Yes, but yes, it is a blow. It is a blow to physics, be honest, to some of the models, be honest. Yeah.
Thank you very much. So let's thank Adrian again. And there's no more questions. I don't see any questions so far. So yeah, let's thank you again.
Goodbye. Yeah, thank you.
And thanks very much for taking the time out of your evening.
Thank you very much, Peter. Now, I think that you have to present Lizardo is the next call. You are mute again.
Yes. Sorry. Okay. So let me just get back to where I was. Sorry, 1 second.
Dr. Lizardo, I don't know if you are ready, so you can start sharing
Are you
your
ready,
screen.
Gustavo?
Yes, I'm ready. Do you want me to share my slides?
Yes, please. So, okay. So, welcome, Lizardo. So yes, so sorry, I don't have your semblance, but so Lizardo will talk on latest results on high energy heavy ion collisions with the CMS experiment at LHC. Sorry.
Okay.
Thank you very much.
Ok, so, bueno, primero que nada, no sé, como estoy viendo que hay muchos personas conectadas que me parece que son estudiantes, bueno, entonces voy a cambiar a idioma español, no hay ningún problema, o prefieren que sea en inglés.
No, it's fine in Spanish. They can, people who, if there's anyone who wants to watch the talk and doesn't speak Spanish, they can put the captions on Zoom and have the automatic translation.
Bueno, ok, bueno, entonces, repito, pues sobre todo me parece que hay estudiantes, entonces por eso voy a hablar en español. Entonces, bueno, yo voy a presentar, bueno, resultados recientes sobre física de colisiones pesados en el experimento CMS del LHC. Vamos a empezar con una breve introducción de lo que es el modelo estándar. Sí, el modelo estándar de las partículas elementales las podemos dividir en dos grandes grupos. Están los bosones y los bosones aquí en las dos columnas de la derecha y los fermiones, tres columnas de la izquierda, ¿sí? Donde la diferencia, como me imagino que saben, ¿no? Es que los bosones tienen spin entero y los fermiones spin fraccionario, ¿sí? El modelo estándar incluye tres fuerzas fundamentales que son la electromagnética, bien conocida por todos nosotros, la fuerza electromagnética, perdón, que está mediada por el fotón, la fuerza débil, que es la responsable de los decaimientos radiactivos, ¿sí? Por ejemplo, el bien conocido el decaimiento beta, ¿sí? está, es propagada por el bosón Z y W. Y finalmente la fuerza fuerte, que es la que mantiene a los quarks atrapados dentro de los hadrones, es mediada por el gluón, ¿sí? Ahora bien, dentro del modelo estándar, la fuerza débil y la electromagnética se encuentran unificados en una fuerza que se conoce como la fuerza o la teoría electrodébil, ¿sí? Y la fuerza fuerte, bueno, aún no está muy bien comprendida del todo. Y bueno, entonces la teoría cuántica que él estudia es la cromodinámica cuántica QCD, ¿sí? Y bueno, 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 y me faltó mencionar el Higgs, el bosón de Higgs, bastante famoso. Bueno, el bosón de Higgs es la evidencia del mecanismo de Higgs, que es el que proporciona masa a las partículas, ¿sí? Eh, Hay muchas preguntas que el modelo estándar no puede responder. Esta plática no es sobre esas preguntas, ¿sí? Que el modelo estándar no puede responder, ¿sí? Pero bueno, quería dejar en claro bueno, el modelo estándar es una teoría incompleta, vamos a decirlo, ¿ok? Bueno, este es el diagrama de fase de QCD, ¿sí? En Y tenemos la temperatura, ¿sí? Y en el eje Y tenemos la temperatura y en el eje X tenemos la densidad bariónica, ¿sí? Que es básicamente el número de partículas menos el número de antipartículas, ¿sí? Y bueno, tenemos aquí un punto negro que es en el eje X igual a 1, ¿sí? Básicamente es el régimen de la materia nuclear ordinaria de la que vivimos, con la que convivimos todo el día, ¿sí? Todos los días, ¿sí? Y en esta región que aparece como un semicírculo blanco, indica la región es un gas hadrónico, donde ahí pueden ver más o menos unas bolitas con unos círculos de colores, dos o tres, que quiere decir es la región donde la región de este diagrama de fase donde los quarks y gluones se encuentran atrapados dentro de los hadrones, que es así como los conocemos hoy en día. Sin embargo, ¿sí? Fuera de esa región semicírculo blanco pueden ver que hay algo que se ve en color naranja que dice quarks y gluones o que es un estado de la materia que se conoce como plasma de quarks y gluones, donde los quarks y los gluones, sí que nosotros conocemos que están atrapados dentro de los hadrones, como por ejemplo los protones y los neutrones, en esta región ¿cómo se llama? En naranja, se encuentran libres, ¿ok? Y aquí pueden ver, aquí junto al eje Y, dice el universo temprano, ¿sí? Pues como se encontraba, como lo dice el nombre, a los primeros instantes después del Big Bang, donde la densidad bariónica era muy pequeña, ¿sí? Donde prácticamente había una igualdad entre materia y antimateria, ¿sí? Y a muy altas temperaturas, entonces uno puede, en esos primeros instantes del universo primitivo, se encontraba gobernado por el plasma de quarks y gluones, ¿sí? Y bueno, conforme el universo se fue expandiendo y se fue enfriando, bueno, pues los quarks y los gluones empezaron a quedar atrapados, ¿sí? Dentro de los hadrones. Ahora bien, en el laboratorio, ¿sí? Nosotros podemos recrear esas condiciones que tenía el universo temprano por medio de colisiones de iones pesados, ¿no? Como aquí lo dice, por ejemplo, en esta flecha roja dice, bueno, dice dos aceleradores RIC, que significa Relativistic Heavy Ion Collider, y el LHC, que es el gran colisionador de hadrones, del cual me voy a enfocar, ¿sí? Entonces, repito, por medio de colisiones de iones pesados a muy altas energías, nosotros podemos recrear este universo temprano y por lo tanto acceder a este plasma de quarks y gluones. Sin embargo, el plasma de quarks y gluones tiene una vida, un tiempo de vida extremadamente corto que no lo podemos estudiar directamente, así que nos valemos eh, de sondas o de mecanismos indirectos, ¿sí? Por ejemplo, uno es el estudio del quarkonium. Quarkonium, se me olvidó mencionar, sí, son partículas formadas por un charm y un anti-charm, o bien un bottom y un anti-bottom, ¿sí? Entonces, estas partículas, el charm y bottom, son sobre las que me voy a enfocar en esta plática, ¿sí? Entonces, el quarkonium en particular, la J-psi, es una partícula que está compuesta por un quark charm y un anti-charm, sí fue propuesta en la década de los 80 como una herramienta para el estudio del plasma de quarks y gluones. ¿Por qué? Porque se produce en los primeros instantes de la colisión, ¿sí? Y además cuando ocurre este desconfinamiento de los quarks y los gluones en el plasma, entonces sufren lo que es el apantallamiento de Debye, de tal forma que este estado originalmente ligado de 6 barra, ¿sí? Eh, eh, pues por decir, bueno, se rompe esa ligadura de tal forma que lo que originalmente era una JEPSI, pues ya no es una JPSI y por lo tanto hay una disminución o supresión de la producción de estas partículas JPSI. Además, a inicios de los años de la década de los 2000, bueno, se predijo que esta supresión, bueno, no aplica solo para la JPSI, sino para todos los estados del quarkonium, de tal forma que los estados excitados se rompen, ¿sí? A diferentes temperaturas del plasma, dando lugar a una supresión secuencial, como por ejemplo, aquí lo vamos a ver, por ejemplo, la Psi2S, que es un estado excitado y tiene una energía de ligadura menor que la JPSI, pues se puede disociar a una temperatura cercana a la temperatura de desconfinamiento, mientras que las otras partículas, por ejemplo la JPSI, sigue sobreviviendo. Y si aumentamos la temperatura del plasma hasta 2 veces la temperatura de desconfinamiento, entonces ahí ya hay una supresión de la JPSI y por lo tanto los estados de quarkonium pueden servir como un termómetro para el estudio del plasma de quarks y gluones. Sin embargo, sí, es cierto también que en el LHC, al tener una energía en el centro de masa bastante grande, te llegan a producir, por ejemplo, muchos de quarks C y C barra. Por lo tanto, esto puede dar lugar a una nueva forma de producción de las J, ¿sí? Por medio de regeneración. Esto es lo que muestro en esta imagen. Por ejemplo, aquí los puntos rojos que están juntitos eran estados de JEPSI que fueron disociados por el apantallamiento de Debye. Sin embargo, son tantos que cuando se enfría y se expande este plasma, pues pueden volver a juntarse, ¿no? Un charm que estaba por aquí y otro charm que estaba del otro lado, pueden juntarse justo al momento de hadronizarse y formar una JEPSI, ¿sí? Y eso quiere decir, es una formación de JEPSI por recombinación. Perdón. Y finalmente, bueno, por ejemplo, los sabores pesados abiertos, que son aquellos que están formados por un charm o un quark beauty, ¿sí? Más un quark ligero como es el U, el D o el F, ¿sí? Estos sabores pesados abiertos al atravesar el plasma de quarks y gluones, sufren el efecto del el dead cone, ¿sí? Que es más o menos el siguiente. Por ejemplo, aquí en esta imagen hasta abajo a la izquierda simboliza un hadrón ligero, por ejemplo, un pión o un protón, ¿sí? ¿Sí? Entonces, al propagarse dentro del plasma, sí, aquí generan una onda de choque este cono que ven aquí, que tiene una pérdida de energía que va como la masa del quark entre la energía, ¿sí? Entonces, el, esta partícula emite radiación de Bremsstrahlung, ¿sí? En toda la región excepto adentro de este cono, ¿sí? Ahora bien, en el caso del charm, ¿sí? Del charm, que es, que es más masivo que estos quarks Us y Des, ¿sí? Entonces el radio del cono aumenta, ¿sí? Por lo tanto, la radiación emitida por esta partícula está restringida, ¿sí? Entonces, ya no puede emitir radiación por todos lados, sino está restringida a no emitir radiación donde esté este cono, ¿sí? Y por el caso del quark B, ¿sí? Entonces el radio del cono aumenta, ¿sí? Porque repito, va a proporcionar la masa de la partícula, ¿sí? Y por lo tanto, la emisión de la radiación es menor, ¿sí? Entonces, esto quiere decir que para las partículas ligeras debe haber una pérdida de energía mayor, mucho mayor que estos quarks pesados, ¿sí? Ya esto es a lo que se conoce como el efecto del dead cone, ¿sí? Bueno, pero bueno, para estudiar colisiones protón-protón, que diga, de iones pesados, también necesitamos hacer estudio de colisiones protón-protón. ¿Por qué? Porque nos sirven para poner a prueba modelos de QCD, ¿sí? Y porque nos sirve para calcular el factor de modificación nuclear, que básicamente, en palabras sencillas, en el numerador es el número de partículas que se producen en colisiones de iones pesados divididos por el número de partículas que se producen en colisiones protón por un factor de escala, ¿sí? En este caso es el número de colisiones, ¿sí? Binarias, o también es estas, ¿sí? O el número de participantes. Ahora bien, ¿qué es esto? Este número de colisiones binarias o de participantes es una medida de la centralidad de la colisión. Si, por ejemplo, aquí tengo un ion pesado, por ejemplo, un plomo, que va a chocar contra otro plomo. En rojo tenemos el número de participantes, ¿sí? Y como ven, conforme más central es la colisión, ¿sí? Conforme el centro de ambos núcleos de plomo está alineado, pues el número de participantes aumenta, ¿sí? Y por el contrario, si esta colisión es periférica, ¿sí? Entonces el número de participantes que estarían en rojo serían solo unos poquitos, ¿ok? Entonces, este número de participantes o el número de colisiones, ¿sí? Porque pues también, ¿no? Si una colisión es central, pues claramente aumenta el número de colisiones entre los protones y los neutrones, ¿sí? Es una medida de la centralidad de la colisión. ¿Ok? Bueno, entonces es el experimento en el que yo les voy a hablar, es el Gran Colisionador de Hadrones, LHC, que se encuentra en la frontera entre Francia y Suiza, ¿sí? Bueno, el LHC en realidad no funciona por sí solo, sino hay todo eh, un complejo de aceleradores, ¿sí? Que le van proporcionando los protones y los iones pesados, ¿ok? Y en el LHC existen 4 grandes experimentos: ALICE, Atlas, CMS, bueno, CMS y LHCb. Y bueno, yo me encuentro participando en CMS y es del cual les voy a hablar. Bueno, rápidamente para los resultados necesitamos dos conceptos. Por ejemplo, en el caso de la JPC, diferenciar entre JPC del tipo prompt y las non-prompt. Las prompt son las que se crean directamente del punto de la colisión, ¿sí? Y las non-prompt son aquellas que se encuentran fuera del punto, que se producen fuera del punto de la colisión debido al decaimiento de una partícula, que vienen del decaimiento de una partícula más pesada, más masiva. Por ejemplo, aquí en esta caricatura de non-prompt, ven que en la colisión se produce un mesón B y este viaja y después decae en una JPC. ¿Ok? Bueno, entonces ese es el prompt y non-prompt. Bueno, como este estudio está bastante interesante, que me parece, por ejemplo, es un ejemplo de por qué nos interesa estudiar colisiones protón-protón, por ejemplo, en el caso de JPC, que dentro de jets, ¿sí? Los jets son chorros de partículas bien colimadas que salen hacia una dirección y dentro de esas pedimos que haya un cc barra, que es una JPC y lo estudiamos en función de esta variable z, que es el cociente entre el momento transverso de la JPC y el momento transverso del jet. Entonces, como la JPC pertenece al jet, entonces este cociente va entre 0 y 1. Bueno, entonces este resultado de LHCb ¿sí? Muestra los datos experimentales en morado y en rojo es la predicción de Pitya, que es un generador de eventos que contiene a Leading Order, ¿sí? Que ya la plática anterior habló de esto. Leading Order de NRQCD, Non-Relativistic QCD, ¿sí? Que es un modelo de la producción de estas partículas. Bueno, entonces aquí como pueden ver, pues de más o menos de SETI entre 0 y 0.6, pues hay más o menos puede describir los datos experimentales, pero de plano de Z.7 hasta 1, pues pueden ver que la predicción del generador de eventos pues es bastante errónea, ¿no? Este resultado luego fue reproducido, fue hecho otra vez por TMS, ¿sí? A una energía diferente. Y bueno, de hecho, el resultado de CMS, pues es un poco, pone en tensión, por decirlo así, el modelo de Pitya con los datos experimentales. Pues nuevamente estos están en morado, ¿sí? Mientras que aquí, bueno, lo que hay que comparar es el prompt de Pitya, porque esto es prompt GPSI en la línea roja. Entonces pueden ver que, pues, por ejemplo, pues ya a partir de, en todo el rango, pues, por ejemplo, de 0.7 para abajo, pues hay un factor de, pues, no sé, como de 4, ¿no? De diferencia entre la línea roja y los datos experimentales. Pero para Z cercano a 1, pues el factor de diferencia es pues prácticamente 8, ¿no? Entonces, pues bueno, aquí es un ejemplo de por qué también nos interesa hacer estudios en colisiones protón-protón, ¿no? Pues porque es una forma de poner a prueba los modelos teóricos, ¿sí? Ahora sí, pasando ya a resultados en iones pesados, pues por ejemplo, aquí tenemos el factor de modificación nuclear. Les recuerdo que es básicamente la producción de las partículas en colisiones nucleares dividido por la producción de partículas en protón-protón por un factor de escala, que en este caso es el número de participantes. Les recuerdo, número de participantes pequeño significa una colisión periférica y número de participantes grandes es una colisión central, ¿sí? Como les mencioné, bueno, aquí tenemos la JPC en colores rojo-naranja y la Psi2S. La Psi2S, también les mencioné, es un estado de ligadura, tiene un estado de ligadura más débil y por lo tanto es más fácil de disociar. Y esto se observa pues que el factor de modificación nuclear, que básicamente nos habla de cómo la supresión pues la J-psi tiene, la psi 2s es sistemáticamente menor que la J-psi, ¿sí? Eso quiere decir que, bueno, eso quiere decir, ¿no? Que hay una mayor supresión de la psi 2s y también es notorio que la J-psi, la supresión de la J-psi aumenta conforme aumenta la centralidad de la colisión, porque quiere decir que hay una mayor densidad de energía disponible aquí, ¿sí? Entonces, aquí estamos ante el caso de una supresión secuencial, que es el caso del termómetro ese que les puse al principio como una animación, ¿sí? Luego tenemos estos dos casos también son de la J-psi, uno en rojo que es una supresión que aumenta conforme aumenta la centralidad de la colisión y otro que es pues prácticamente no hay supresión porque es prácticamente constante. De hecho, conforme aumenta la centralidad de la colisión, pues esto pues aumenta, ¿no? Entonces, a primera vista podría parecer raro, ¿sí? Pero aquí la diferencia es el régimen del momento transverso al que son tomadas las mediciones. Para alto momento transverso, ¿sí? Vemos el mismo comportamiento que aquí, ¿sí? Una supresión de la J-psi que aumenta con la centralidad, que es el caso una supresión secuencial, ¿sí? Pero para bajo momento transverso vemos que como que medio empieza a decaer, pero luego aumenta. Y esto ejemplifica el caso de las jet size que se forman por regeneración. ¿Por qué? Porque conforme aumenta la centralidad, aumenta el número de producción de partículas de Cc barra, de quarks Cc barra, y entonces en vez de que haya esta supresión, ¿sí? Repito, hay esta recombinación de J-psi. ¿Ok? Luego, aquí en esta siguiente diapositiva, les muestro la comparación entre estos dos aceleradores que les había comentado. RIC, ¿sí? Que funcionaba a una energía en el centro de masa de 200 gigaelectronvolts, y el LHC, que funciona a una energía 20 veces mayor, ¿sí? Entonces, esto también es de la J-psi, y como pueden ver, en RIC se tiene un comportamiento de una supresión secuencial, es decir, que la supresión aumenta conforme aumenta la centralidad de la colisión, mientras que en el LHC se tiene ¿cómo se llama? Este comportamiento que pues, la firma, ¿no? De una formación de J-psi vía secuencial, ¿sí? Y entonces aquí la diferencia es la energía en el centro de masa. La energía en el centro de masa en RIC de 200 gigaelectronvolts, pues no es lo suficiente como para generar tantas quarks Cc barra, ¿sí? Y por lo tanto solo le queda la opción de una supresión secuencial, ¿sí? Mientras que en el LHC, como ya dije, la energía del centro de masa, al ser 20 veces mayor que la de RIC, pues produce una enorme cantidad de quarks Cc barra y por lo tanto da pie a esta formación de jet side por vía secuencial. Y bueno, finalmente les había mencionado, bueno, solo les había hablado del caso de charmonium, pero también hay botomonium, es decir, de mesones formados por B y B barra, ¿sí? Aquí tenemos la familia de la upsilon, la upsilon 3S es la que tiene una ligadura mucho menor que la 2S y a su vez menor que la de 1S. Entonces, por el mismo caso de aquí de la psi 2s y la J-psi, pues entonces uno espera que la 3s esté más suprimida que la 2s y esta que la 1s. Y justamente es lo que vemos, ¿no? En verde tenemos la psi 3s, luego tenemos que está más suprimida que la 2s y esta está mucho más suprimida que la 1s. ¿sí? Y en este caso tenemos un escenario de una supresión secuencial, que es la del termómetro. Aquí no hay la formación de upsilon por recombinación, ¿sí? ¿Por qué? Pues porque los quarks B son 3 veces más masivos, mucho más, perdón, mucho más masivos que como un factor de, no sé, como 7 veces más o menos, más masivos que los quark charm, y bueno, pues no hay tanta producción de quarks B para que haya una regeneración de upsilons por medio de recombinación. Bueno, y finalmente, ya para terminar, esta es la última gráfica de sabores pesados abiertos, ¿sí? Donde les comenté sobre este efecto del dead cone. Y bueno, entonces en gris tenemos los quarks, los hadrones ligeros, que son estos de este caso. Vemos que son, pues, los que están bien, tienen mucha menor supresión, ¿sí? Para esto en función del momento transverso, que los azules, que son los azules estos, que son los del quark charm, ¿sí? Y bueno, a un PT intermedio, que es esta región que estoy sombreando, bueno, los quarks, los hadrones grises, que son los ligeros, pues están, bueno, ahí más o menos con la misma supresión que los quark, que los hadrones charm, ¿sí? Que están formados por partículas charm. Y aquí sí se observa el efecto del dead cone. ¿Por qué? Porque los rojos y los amarillos son aquellos que vienen del decaimiento de un mesón, básicamente un mesón o un hadrón B. Entonces, aquí a PT intermedio sí se observa el efecto del dead cone, pero conforme aumentamos el PT, pues vemos que prácticamente todos los puntos presentan la misma supresión, ¿sí? Bueno, entonces ya con esto quiero terminar, me voy a saltar esto. Y bueno, en resumen, aún tenemos un largo camino que recorrer para tener un modelo estándar completo, porque repito, el modelo estándar de hoy en día es un modelo incompleto, no responde a muchas preguntas que no son, esta plática no es sobre eso, pero bueno, eh, el plasma de quarks y gluones se puede recrear en el laboratorio por medio de colisiones de iones pesados. El quarkonium y los sabores pesados abiertos son una herramienta muy útil para el estudio del plasma de quarks y gluones. Se ha observado un escenario de supresión secuencial para el quarkonium, pero en el LHC, pero también una formación de Gibbsite por regeneración. Y para los separados pesados abiertos, el efecto de dead cone solo es visible a un momento transverso intermedio, a un rango de momento transverso intermedio. Y bueno, eso es todo. Gracias por su atención.
Muchas gracias, Lizardo. Entonces, ¿quién tiene preguntas para Lizardo? No sé dónde puedo ver.
Yo tengo una
Marco.
pregunta. Hola, Lizardo, buenos días. Bueno, pues, gracias por tu plática, estuvo muy interesante. Yo tengo una duda, porque recientemente salió, bueno, en algunos trabajos, que hay un candidato a toponium.
Exactamente, sí. Bueno, efectivamente, ¿no? O sea, digo, bueno, eh, los únicos hasta ahora que se han medido como estados ligados, ¿sí? De onium, ¿sí? O sea, de quarks pesados, ¿no? Los quarks pesados, ¿no? Pues para la gente que nos escucha, son charm, bottom y top, ¿sí? ¿sí? Ahora bien, en principio, bueno, el charm y el bottom, pues ya les acabo de mostrar, forma estados ligados, ¿sí? El top, en principio, tiene bueno, es muy masivo, de hecho, por ejemplo, si lo comparamos, el bottom es como tiene de una masa de, bueno, aquí dice 4, normalmente es 4,5 o 5 yo lo he tomado en mis trabajos, ¿no? Bueno, y mientras que de 5 GB, mientras que el top es de una masa de 175 GB, ¿no? O sea, ahí hay un factor como de 30 más o menos, ¿no? O 30, 35 más o menos, ¿no? Entonces, debido a su masa tan grande, el tiempo de vida del top, ¿no? Porque es inversamente proporcional a la masa, entonces es muy pequeño y no alcanza, y el tiempo de vida es mucho menor al tiempo requerido para hadronizarse, ¿sí? Entonces, lo que se ha medido ahorita es que hay un exceso, ¿sí? Primero lo midió CMS y hace como un año, y justo hace unas semanas lo acaba de confirmar Atlas, ¿no? Entonces, hay un exceso de pares de top, o bueno, de tops y anti-top en el rango de masa donde uno esperaría o sea, un estado ligado de top anti-top, ¿sí? Entonces, eso efectivamente lanza como que la pregunta, ¿no? De que si en realidad sí se están formando o no se están formando estados ligados de toponium, que se le llamaría, ¿no? Entonces, bueno, pero bueno, bueno, hasta ahorita al menos, repito, queda en un exceso de cuentas, pero no es tanto tal cual que se observe un estado ligado. ¿Me explico?
Ah, ok. Sí, sí, muchas gracias. Entonces, todavía en colisiones, hay un zancudo. En colisiones en iones pesados, no se ha visto nada parecido, ese tipo de exceso.
No, 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 no. En yo pesado, no, 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 no. No.
Ah, ok. Sí, sí, muchas gracias. Esa era mi pregunta.
Bueno, ¿alguien más tenía una pregunta a realizar? Bueno, si no, pues, muchas gracias, Lázaro, por la muy buena práctica, pues, gracias. Y, si entiendo bien, ya tenemos un descanso de media hora, ¿no? ¿Estoy bien, Marco?
Sí, 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 hay un descanso de media hora, pero nada más tengo un aviso para los participantes que no, que solamente están asistiendo y no van a dar una plática. Justo en este momento les estoy compartiendo un enlace de una encuesta donde se les pide nombre, correo e institución en caso de ser necesario para que se puedan preparar sus constancias. Quienes van a dar una plática y ya la registraron, les va a llegar al correo, ya ahí donde se les avisó. Y también, bueno, hemos tenido problemas con la traducción y vamos a tratar de corregir eso ahorita instalando una aplicación que les compartí, Vitor Translate. Entonces, ahorita en unos minutos ya el host lo va a habilitar. Y, y bueno, para poder traducir, porque ahorita nada más los subtítulos aparecen en el idioma en el que se habla. Y la idea era una especie de subtítulo bilingüe. Entonces, les invito instalar esa aplicación aquí en Zoom y espero pronto que se pueda activar aquí. Entonces, ok, vamos a tomar media hora de descanso y volvemos a las 12. We are going to pause to pause or conference, and we will be back in 30 minutes. So we can have some lunch or appetizer. So we'll be back in 30 minutes. So please do not disconnect. The next call will be presented by Ana Julia Miser. So nos vemos en media hora. We'll be back in 30 minutes. Alexis, no